day 3. Now I request Engineer K. Udayakumar, AP Department of EEE, to introduce our chief guest.
Thank you, ma'am. Good evening, sir. Engineer G. Rajaganesan is a solar energy professional with over 12 years experience in the solar photovoltaic sector. He holds a BE in electrical and electronic engineering from Anna University, Chennai, and began his career at Bell Corporate R&D, later moving into academia before establishing himself as a solar technocrat. He currently serves as Director Technical Operation VATIO Energy India Private Limited and Chief Technical Officer at Tamil Nadu Advanced Technical Training Institute. His expertise in solar PV system design and integration, rooftop and ground-mounted plants, off-grid and grid-tied system, EV charging infrastructure, and green hydrogen project, along with government fund project execution and skill development innovation. He has guided 30 projects for 6 research projects and 12 consulting assignments, participated in 15 national and 5 international conferences, and delivered 10 project demonstrations. He has also organized 12 workshops, 4 conferences, 5 faculty development programs, 25 seminars, 22 short-term courses, and 28 training programs, and has served as a resource person for 45 technical meets, contributing significantly to capacity building and industry academia collaboration in the renewable energy sector. Thank you, sir.
Respected sir, now we are handing over the session to you, sir.
Sir, Rajaganesan, sir, please take over the session, sir. जी सर co-host please make me as a co-host. CS के सर को पूरा Sir, please check it, sir. If you are act as a co-host, sir.
I think, yeah, I got it.
Okay, sir. Thank
Very
you,
good
sir.
evening. Yeah, thank you. Thank you very much. Very good evening, one and all. And I thank for organizing, I thank you all for organizing this event. And it's a sponsored program from government. And thanks for the government. And also, can able to see a very good number of participants here. Of course, the title of the program is Need of the Hour, and also it's an upcoming field. And the green hydrogen is something which is less discussed in the industry and also in the academia. for a long time, and that is the right time to discuss on all these things. And also, how practically implementing the green hydrogen technology as a product, as a system in our premises, and also how much energy efficient, how much it is cost efficient, how much it is going to be reliable, in terms of reliability, how long it is going to last. It's all a point of question, but definitely every technology over a point of time will will get its own maturity, and it will evolve by its own. So similarly, we can expect the green hydrogen also like that. So today, my session is going to talk more about integration of solar PV system in green hydrogen production and its cost economics. And before that, I just want to take you a quick journey into the green hydrogen technology, how it is being prepared and all. So just wanted to know, like, in the previous sessions or in the forthcoming, like, you have any specific technology, specific sessions to talk about this in detail? So is there any session planned to talk about green hydrogen production in detail?
No, they have just breached the topic, sir. That is, different types of hydrogens available, like pink, green, and gray, and how renewable system has been into green energy production. They didn't go in deep into the subject, sir.
So how green hydrogen is being prepared, or how it evolves, what is the procedure involved, and that's not discussed yet.
No, no, sir, not it, sir.
Okay, I think this presentation really makes you a better clarity about what it is. And I will divide the system into, my session into two parts. One is to discuss about the green hydrogen technology, and parallelly, I will shift it to the solar part, like how we can able to integrate the solar PV in the green hydrogen production.
Sure,
Okay,
sir, sure.
so let's get into the presentation. So before I want to talk about the green hydrogen, what is this green hydrogen? Green hydrogen is nothing but the production of hydrogen happens by utilizing the power from green energy sources. That's why it is referred as green hydrogen. Why? Because the the major fuel, the major energy which is going to consumed in the production of hydrogen is electricity. So if the major consumption of the production process is going to come from a clean and green source, then definitely it can be called as a or referred as a green product. That is why it's referred as a green hydrogen. Otherwise, it's a regular hydrogen being produced out of the regular process. Okay. Now we get into the much more verticals of hydrogen and its storage. So if you see the hydrogen, first we need to talk about, before talk about the production, we need to talk about how the hydrogen storage is plays a very important role, and how what are the physical challenges. So you can see wide classification of methods that we can able to have. So presently the hydrogen is being stored in the pressure vessels like type 1, 2, 3, 4. There are four types of pressure vessels where we can have the hydrogen which is get compressed. So basically, hydrogen is a low volumetric energy density and lightest of all the elements. So basically, it's very difficult to store in an compartment. So it's very lighter than the helium and also easily lost into the atmosphere. So that's one bigger challenge. And also its low boiling point, which is minus 252 degrees Celsius. So it has to be kept in a very low temperature, like the cryogenic way. And storing hydrogen as a gas is really requires a lot of high pressure tanks. So basically, 350 to 700 bar pressure is required to keep that thing inside. And definitely, why the hydrogen is critical? and storage of hydrogen, because with hydrogen there are a lot of applications you can utilize in the upcoming days by incorporating that with a fuel cell, and also the usage of hydrogen in various methods, various technologies. It is going to make the process much more clean and green, and much more less pollution, and also more efficient. Okay, and hydrogen cooling is something which is already there in place, which works very efficient. And the leak detection of hydrogen systems is another much more challenge when it comes to why hydrogen technology is still far more distance from what we think. Okay, so let's get into much more in detail about this. So that's one thing, and for the safety purpose, the hydrogen can be stored even under the ground. So by using the different technologies like salt cavern, exhausted oil and gas fields, they can use to have a big area under that, and hydrogen is stored under that. So there is no point of escape of hydrogen from the bottom to the up, because it's completely the terrestrial area. So this is another technology method where we can able to store the hydrogen. And as I told, there are four types of hydrogen storage here. So type 1, type 2, type 3, and type 4. So if you see here in detail, the pressures of hydrogen storage, type 1 it is 200 bar, type 2 is 300 bar, type 3, type 4, and type. So up to 1000 bar pressure, type 4 tank can able to have. So there are different lining material which is there inside. I'm getting a cross noise from
Participants, kindly mute your mic, please. Sorry for the disturbance, sir.
no problem. So the type 4 vessels is the a high vessel which can have able to have a high pressure hydrogen storage, and that's made up of all carbon fiber with inner line of polyamide and polyethylene plastic, and it's much more lightweight and having very high strength, and but it's expensive. So let's get into much detail about the Type 4 vessel. So this is the setup of Type 4 vessel, how it looks with by using the carbon fiber composite, and there is a dome protection, there is a valve, and there is an inner line, and there is a temperature sensor inside that. See, the point is, unless otherwise the hydrogen storage methodology or the technology is being fully developed and implemented, this technology is very challenging and risky and more complicated to deal with. So that's why the and hydrogen storage plays an important role when you come and talk about the green hydrogen technology and its usage. So these are different types of cylinder testing process which is involved in the hydrogen storage. So you can see that anyway the presentation will be shared, so you get to know all about things. So it includes the what type of resin material is used, plastic liners is used, then hydrostatic burst pressure test, ambient pressure test, then leak test, bonfire test, penetration test, chemical exposure test, then damage test, then torque test. All the test has been done before it is going to be get deployed. And transportation of hydrogen is a very critical point, because usually the petrol, diesel, crudes can be easily transferred from one point to another point with heavy containers. And there is a petrol SS, of course, it will evaporate easily. But again, it's not that much complicated in terms of its safety and other things. Whereas diesel is not that much to be worried about, and as well as crude. But when it comes to the hydrogen transportation, which is something very looked upon very keenly, because there is two stage. One is the physical storage, and this is the chemical storage. So in physical storage, it is get compressed and it is being stored. In chemical storage, it will be transformed into different forms and it is stored. So the mode of transportation, it can be taken in the trucks, rails, pipeline, and shipping, and the travel distance is also defined. So you cannot go even more than that. There is a point like if you want to go for a larger distance of thing, then only you can be able to go for shipping because travel making the hydrogen to be get traveled in the shipping involves a much more complexity because the ship will have a lot of shakes in the journey and that makes a higher possibility of hydrogen to get leaked. So basically the hydrogen was transported from Europe to Japan. The moment when the container reaches Japan, when they open that, there is nothing inside because every hydrogen got leaked. It's very difficult to store the hydrogen. So that kind of serious issues are there in terms of storing it. And yes, it's given like how the hydrogen can be stored and what is the kind of energy density we can have. Okay, so with respect to the compressed liquid, then other forms of metal hydride and borohydrides. So this is the storage volume of hydrogen in terms of the tanks. If you see 11,000 liters, 1,400 liters, 24 liters, 14 liters. So 14 liters is the liquefied form. Yeah. So shipping of hydrogen from one point to other point will involve a lot of logistics and transportation thing. And whereas the liquid hydrogen or ammonia is normally transported in the ships due to their high energy density and high cost due to the very conversion charges. Because if you once change the form from one to other, then again you have to convert it back to the hydrogen. So ultimately, it is all going to create or increase the costing and also transportation of hydrogen through pipelines. That's also another way, and blending the hydrogen with other natural gases pipelines. That's another way. Ultimately, everything involves the process. So if you see the process involved, then how much of electricity it is going to consume. That's the point. So now we're coming into the main subject of the components of system involved. So if you see, this is the closed loop cooling plant and control room, water purification, fan cooler, power rack, safe zone. This is the hydrogen generator and this is the hydrogen purifier. So this is the total system which is involved. So this is a general generic schematic and balance of a plant for power generation. So you have see this is the transformer where the supply is coming and it gets converted into DC through a rectifier. So you can able to see here, right? So this is the input supply for the electrolyzer. So basically the input, the fuel for this whole process is water. So water is fed into the electrolyzer and the supply is given to the electrolyzer through the rectifier because DC power is required for the electrolyzer to work. So basically this electrolyzer work in such a way so that it will separate the H2O, that's water, into two separate components. One is the hydrogen H2, other is the O2. So you can see here, so oxygen is separated and the hydrogen is separated. So oxygen is taken in through unvented oxygen point, whereas hydrogen is taken and it is sent to two various chambers and to separate the water from the gas and dry it so that it will be a dry hydrogen, and after that it is sent to the buffer tank for compression and it is much more compressed to high pressure compressor, and finally it comes to the storage tank. So and it will be stored in that, and the result of this process is a water, okay, electrolyte tank where the water is collected and it is the byproduct of this whole process. So this is the total schematic layout of the hydrogen production process. This is the hydrogen production process. The moment when we call this as a green hydrogen, it's very simple that the power which is fed as an input to the electrolyzer here is coming from a green source. If I'm going to deploy a solar power plant to feed the power to the system, then the whole process is being working on the basis of the power coming from a green source. Then the hydrogen produced out of this process can be referred as a green hydrogen. So that is why it's referred as a green hydrogen. Now you can see the another schematic layout where supply is given to the electrolyzer and hydrogen and oxygen is separated. The same thing in a different arrangement. Right. So the hydrogen generation stages can be classified on transformer rectifier unit. This is the electrical unit which is mainly there in front of the electrolyzer, because this converts the existing alternate current into the DC. Okay. So DC power is required because, and the DC power will power the electrolyzer. Okay. So basically the anode and cathode of the electrolyzer is connected with positive and negative terminal of the rectifier output. Whereas the electrolyte storage will be of consist of two gas separator and electrolyte recirculation system, and it is cooled and is recycled into the stack. So the main function is to feed water tank, cools down the H2, and remove the residual electrolyte traces. So this is the pre-hydrogen generation stages. The post-hydrogen generation stages is the buffer tank, where you collect the hydrogen and get it dried and compress it and ready for transportation. Okay, so that's the H2 compressor, where it will compress and store it in a category 1, 2, 3, 4 tanks based on the nature of transportation, and that's compressed. And once it is stored, then it is taken for further level of transportation. And there are other components like deoxidizer. So that is to remove the other suspended molecules in that. Then hydrogen dryer unit to remove the water vapor and moisture in the hydrogen gas, and storage of hydrogen. And there is another unit called water purification unit, where the pure water which is coming out of the byproduct will be taken out, and we have to remove the contamination of the recycled water to protect the electrolyte stack, because through the process it will go through different pipes and come out. So there might be some microparticles of iron, metal, and other things. So that has to be removed effectively. Otherwise, the problem is the electrolytes have a membrane. Okay, so the membrane is something which separates. So the membrane is very sensitive, and that's the heart of the system. Like how our heart there is auricle and articles and ventricles. Similarly, here the main unit which works for the whole subject is the electrolyzer membrane. So the main purpose of filtering and purifying the water is to increase the longevity of the electrolyzer. So, so these are different types of energy required for purifying 1 cubic meter water for electrolysis process. So if the water is from the groundwater, then it only requires 2 units, and if it's a treated wastewater, then it requires 2.2 units. And if it is a seawater, it requires 7 units. And out of this electrolysis process, then the amount of energy required for 1 cubic meter of water, the whole process is going to generate the hydrogen, and that can be used for generation of power later by giving it to the fuel cell. So this is the wastewater treated in the green hydrogen process. So first is the groundwater, where the sand filtration and aeration will be done. And is there any, if it is a chlorinated city water, then activated carbons can be used. If it is a treated wastewater or surface water, then we can use ultraviolet and UV filtration. If it is seawater, then we have to go for a desalination process to remove it. After that, then there will be multiple stages of softening the water, demineralization of the water, degazing and polishing and this thing. Under that, finally the ultra pure water is ready for electrolysis. After this 8 stages, after this 4 stages from the various different forms of water source, the filtered treated water will only allowed to be taken for the input for hydrogen production. So now comes to the main subject of the topic today is the power source for electrolyzer. So how the electrolyzer will work, what is the essential thing required is to operate the electrolyzer, the main fundamental is power. So the electrolyzer works on the DC supply and that requires a DC from system. But unfortunately, the main source which is available in our grid network is an AC. So that power needs to come from your existing conventional grid. And the major consumption of cost in hydrogen production is the electricity cost. So the moment when we look after some technology, some system which can able to cut down the cost of electricity in a production process, then the cost of product will substantially come down. Okay, that's the whole idea of why we need to go the hydrogen process as a green hydrogen is to reduce the kind of pollution of air, water, land in any means, okay, or noise in a great way so that the hydrogen, because anyway, hydrogen production by itself a costly process. In the costly process, we are going to utilize and we are going to emit or suspend a lot of unwanted items into the atmosphere, then it is brutally a very worst way of manufacturing something. So that's why it's better to go with a system which is so clean and green. And that's where the idea of integrating the green energy sources as the source for electrolyzer process. Because the moment when we go for the large scale production of hydrogen, then we need a continuous power, and if that comes from the conventional sources like thermal power plant or any of the gas powered power plant, then it doesn't make any sense because you are burning coal somewhere, emitting carbon somewhere, and claiming this as a clean green energy doesn't make any sense. That's why other hydrogen forms are given as gray hydrogen like that. So here it is referred as green as because this can be the power coming out of this is from a green source. So the green energy can be from wind, solar, or hydropower and other renewable, or it can be hybrid with wind and solar and battery. Okay, so basically the electrical installations transform voltage from high to medium to low by means of transformers, because in a high power transmissions, the voltage levels are high. It can be a to 440 kV, 220 kV, 110 kV. Down the line, it will step down to 66 kV, 33 kV, 11 kV, and finally from the 11 kV, it is step down to our 415 volt three phase supply, and will come to your loads. So here the load is a rectifier. So basically whatever the power comes from the AC, it get converted into a DC, and the DC voltage and current directly, proportional to what is the kilowatt size of the electrolyzer we use. So there will be a 50 kilowatt electrolyzer, there will be a 100 kilowatt electrolyzer. So based on the power consumption of the electrolyzer, that rectifier will be chosen accordingly. Okay, so the rectifier purpose is to convert the AC into DC. So that's what is given. So, and also a few points which we need to clearly look after here is the rectifier will have also result in some kind of a harmonics and energy losses. So that the selection of rectifier is also one important critical factor, where the electrolyzer is operated at lower loads for to handle the negative effect of harmonics, and it's also possible to reduce harmonics and operate at the electrolyzer flexibility. so that we can use the bulk rectifier converter, and but of course it comes at a cost. So here you can see the switchgear, and there will be a harmonic filter and compensation units to reduce the harmonics and make the system harmonic free, and the total harmonic distortion should not be more than 1% for the total system. So making sure that the power factor is also maintained at unity and the harmonics also completely eliminated. So the rectifier can be of different technology. It can be a thyristor based or IGBT based. Nowadays, the solid state device technologies are evolved much better, and we have a lot of active control and harmonic filters adopted inside. So the advanced designs and development for the rectifiers is available up to 3 megawatt power. So that's something huge. And wherever the high currents involved or multiple DC buses involved, and that needs multiple stacks of rectifiers to compensate that. And these are the different types of rectifiers which is used in the process of hydrogen production. So thyristor rectifier, IGBT, and chopper power rectifier. And yes, so here what I have given is the fuel, feedstock, power, and industry wise where and all the hydrogen can be utilized and processed. Now, I want to take you to the real subject of how the solar is going to be implemented and how it's going to be beneficial for you. So, the hydrogen in energy system. So we see the hydrogen can be used. I'm coming to the point of application of hydrogen, and now we shifted to how to integrate the solar into the hydrogen. Before think about what is the necessity of generating hydrogen, because it has multiple advantages and applications, right from transportation, creation of synthetic fuels, then fertilizers, metal production, process, power generation. So many ways, and even including the power generation by integrating with solar, it works very efficiently. So I'm sure we all know about a few technologies like Bloom box and hydrogen fuel cells, the advanced level, where I just read an article way back where a 100-watt panel, solar panel with a small fuel cell can able to generate a power record for a typical normal 2 BHK house for 10 years. So then imagine how efficient the system is going to be. And I don't know like how practically it is possible, but the way the technology they climb this is going to be that much efficient. Like how over the period of years, like we evolved in terms of the camera, in terms of the communication, and now in one phone we have a 100x zoom in a mobile. Having an 100x optical zoom or a digital zoom before will require a huge telescopic lens and other subjects. Now, through the AI, a normal 40 megawatt megapixel camera lens can able to handle 120x of depth. So that's something unimaginable the way the technology is evolving. So similarly, adoption of the green hydrogen technology will make a big breakthrough in terms of energy storage and energy production. And ultimately, the idea is to make the entire process clean energy form. So now, this is the quick glimpse about what is the process involved in the green hydrogen production and the equipments and systems involved in the green hydrogen production and where the hydrogen is going to be used. Now, we will be getting into the main core part of integrating the solar with with the green hydrogen production. I mean, the hydrogen production setup. So let's get into that. So till that, if you have any doubts, you can ask me. So you can participants can put your questions in the chat so that I can try to answer it.
Dear professors, if you have any queries, ask to the resource person. Please unmute your mic, then ask to the resource person.
So if you have any doubts, please definitely you can ask.
Sir, Rajaganesan sir,
Yeah.
please you carry on, sir.
Okay.
Thank you, sir.
Thank you.
Dear participants, if you have any queries, please unmute your mic and ask to the resource person.
So I hope you can able to see the screen.
Yes, sir. It's visible, sir.
So this is the simple nutshell of a 500 kilowatt on-grid system. So in case if the production site requires a system of 500 kilowatt to be powered by solar, then it's going to cost them an additional of 1.75 crore on their capital cost. But if you see the math down the line, the return of investment is just 3 years, which means it works around 30 to 33% rate of return year on year, which you can never ever witness in any of the form of investment. Okay, so the ideology is bringing solar into green hydrogen production is a very very fundamental need of the hour. Not to claim it is green, it's also to make it much more cost effective, because the moment when you bring the solar into the system, first 3 years is going to be your expenditure. From the fourth year onwards, the cost of production is going to come down because the cost of electricity year on year is going to save, which means every year 58 lakhs is going to be the savings, and translating the amount of energy produced in 1 year of time, if you subtract that amount, and that is going to make the cost of hydrogen production in a great way. Okay, so in case today the hydrogen production is going to cost 100%, if you adopt solar, then the cost can easily come down by 30 to 35%, because the cost of electricity required for hydrogen separation, process, compression, the electricity consumption is huge. By the way, if the electricity is going to come at free of cost, then after 3 years, by the way, then it's going to have a big impact in terms of the cost. Okay. So before that, taking into in detail about how the solar can be adopted, we need to look at like what is the type of system involved and how much energy it can able to perform, and what are the kind of environmental benefits that it will help you out. So let us go into that. So we
Sir, your screen is not visible, sir. Rajaganesan, sir.
Sir?
Yeah, now got it. Now got it.
Okay, sir. Okay, sir.
So, in case if you are planning to put a 800 kilowatt for our green hydrogen production, so what are the kind of environmental benefits that we can see here? So, installing a 800 kilowatt system is literally equal to planting 16,000 trees per year. Okay. And also, kind of water which we are going to save is about 20.8 lakhs liters of water saved every year, and also 5.2 lakh kilogram of carbon emissions is prevented every year. So approximately 522 tons of carbon emission has been saved, and approximately 580 tons of coal is being saved every year, and also 130 kiloliters of gasolines is also saved. So ultimately, that's why we are referring generating power through solar as a green power, because this is a kind of environmental impact. Because if you go with the thermal power plant, you need a coal, lignite, and that's a byproduct of that's been extracted from the under the ground. That's nothing but a fossil fuel. Okay, so once upon a time there were tree that's gone into the earth and it's become a coal and further converted into lignite. That's all the story we all know. But the point is, the more we deplete the resources, and the resources will get deficit. And if you see in Neyveli, we have a lot of mines. We took a lot of lignites, and after it's all closed, even if you do the plantation, how long it's going to take for that particular area to be get regenerated? That's a big question. Now, the second point is, to run the thermal power plant, you need to dig out lot of waters for various applications, for pump the water to the boiler, to preheat it, for the chiller plants, for the the cooling towers. Everywhere the water is going to be pumped from the ground and it's going to be utilized. So we all think for the generation of 1 unit of electricity, and how many liters of water is being wasted, how many kilograms of lignite and coal, fossil fuels have been used, and how much of machinery is being used, and how much smoke it is emitting. If you all calculate everything in one go, then the energy produced and we are using is not at all a clean energy. And if the hydrogen is going to be produced out of that kind of an energy, then it is of no point. So we are shifting to hydrogen, thinking in it's going to be a more reliable and efficient and eco-friendly. Okay. So to make it happen, then definitely what source we are going to use is going to be very, very important. So this is the a sheet which makes you a clear understanding about how, how much of energy, how much of environmental benefit because we are going for solar. Now, let's get into much detail about how much energy generation that we can expect out of a plant. So let's have a look at it. So let us take a 100 kilowatt as a case study for your quick understanding. So 100 kilowatt will generate approximately 1,55,000 units, electricity units every year. And the cost savings is going to be approximately 12.4 lakhs units, 12.4 lakh rupee. And whatever the power generated during the daytime, we can utilize that power 100%. Okay. And the lifetime of the plant has been operated for 20 to 25 years based on the thing. Now let us dive much more into the technical aspects of an 100 kilowatt system. So usually solar power plant, what we put is an on-grid system for this kind of application. Either it can be a captive plant. Captive plant is something which is put on over the premises itself. So whatever power generated on the rooftop, that will be utilized on the building itself for the factory or industry or whatever it is. It's consumed during the daytime itself. In case if their consumption is less, then the surplus energy have a possibility of getting exported into the grid. So that is called as feed-in. Okay. So there are two different methods, or there's three different methods which is available in India per se. One is a net metering, other is a net feed-in, third is the gross metering. So net metering is adjustment of units by units. For residential systems, it is there. So if you export 10 units in the day, you can adjust the same 10 units in the night time for your AC consumption. But that's not possible in an industry or commercial establishment where they are forced to adjust only during the time of the day. That's what we call it as TOD. So whatever power produced during the daytime, on the same time that power needs to be consumed. Okay. So the plant has to be designed in such a way whatever the power produced from the solar should be more optimally on the maximum. It has to be utilized on the daytime itself during the load time itself. So for that, understanding the load scenario is very, very important. So that's why when we go for the installation of solar for any factory, industry, or process industries, definitely understanding the load curve is very, very important. So what's their load pattern from morning to evening? What is their peak load? What is their base load? What is their average load? What is the kind of, the on and off patterns which we can able to see in their power? So accordingly, the size of solar power plant has to be selected and that needs to be installed. So basically, whatever the plant which we design, that will be connected to their internal substation itself, and that power get distributed for all the connected loads. So imagine if there is a load of 200 kilowatt and we have a plant of 100 kilowatt. So this 100 kilowatt power will be completely utilized in the existing network itself. The deficit is going to be another 100 because the requirement is 200, 100 is already given by the solar, and the deficit is 100, and that is only going to be drawn from the grid. So whatever we draw from the grid is going to be billed. So straight away in during the daytime, because of solar, we are completely offsetting the requirement from the grid. So that's the thing. And the graph what you're seeing is the monthly production statistics of an 100 kilowatt plant for a Chennai location. So from the Jan to December, the maximum production we can expect in March and April, whereas the minimum production is towards the November and December. So we can expect the performance ratio of 81.6% with an annual generation of 598 units per kilowatt per year. Yeah. So these are the various technical inputs that we need to consider before arriving what is the performance of the plant. So one is the irradiation, other is the energy yield assessment estimation. So irradiation is nothing but what is the amount of sunlight which is available in that area. So basically we have different topographies, different climatic conditions spread across different parts of India. So, if in Chennai it's expected a generation is this much, this won't be the same in Kerala. This won't be the same in Leh Ladakh. Okay, so the the main factor which is going to be get differentiated because of the difference in performance is the source. That's a light. Sunlight comes from the sun. So the kind of climatic situation which is around that area will definitely influence how much of sunlight which falls over that particular area. So if the sunlight is better, then it's directly proportional to the energy production. So if sunlight falls over there is good and it is plentifully available throughout the year, then the production of energy of the plant throughout the year will be high. If it is only during certain time and it won't be available the rest of the year or months, then it's something which needs to be analyzed. So that's why the kind of work what we do is now called as a energy yield assessment study. So under the study, we can able to figure it out how much the plant can generate in if suppose if you are going to install at a particular location. Okay. So and also it will show you how much of energy will be produced, how much energy we can expect year on year. And also there is a factor. Today, if you install a 100 kilowatt plant, it might work 100% efficient, but that's not the case for the next 20 years because every year it is going to have a degradation factor where the performance drops by 1% to 0.7% year on year. So that's because of the LID and PID effects, that's the light induced degradation and potential induced degradation effects. So ultimately, even in spite of the reduction of panel performance over the years, but the cost of electricity is also going to increase year on year. So every day, if you say in Tamil Nadu, the electricity prices are getting increased to the percentage of 4 to 7%, whereas the efficiency drop is only 1%. Still, you save 5% of electricity hike year on year if you go with that. If somebody installs solar today, he is going to effectively get his return in 3 years. Subsequently, the electricity price is also going to go up, which makes his return much more faster than what it has been predicted. Okay. So, how the evaluation of a site can be done? Basically, what rooftops which we plan, we have to first do the rooftop solar array feasibility studies because we need to know where the shadows will come and how much it will impact and all the factors we need to analyze. So that's why the analysis of array and its shadow impacts needs to be done. And also we can mention like where the inverter will be placed and how far it's going to be. And the analysis of solar panel shadow simulation studies is also important because the sun is not something which is there at the same place throughout the year. It is going to shift for different seasons, various climatic conditions, and also for different time. So from the morning to evening, the sun travels from east to west, whereas for the different climate condition, the sun moves from north. Just the objects or disturbances which is on the left side or right side, which means east side or west side of your panel, will have a higher possibility of creating shadow. Whereas the objects which is on the south side of your panel installation area will have higher probable possibilities of creating shadows during the winter seasons. So you can wait for 365 days to analyze how the shadow behave in that area. So that's where the simulation studies plays an important role. So by choosing the location, the automatically the latitude and longitude of the particular location will be fetched, and accordingly the sun path will be taken for reference, and that sun path will clearly tell you where the sun will be at particular time, particular day, particular month. Okay, so based on that we can able to estimate where exactly the shadow will fall. In case if this array what solar panel what we designed is there, and by chance if the shadow is falling over that, then definitely it is going to create a substantial amount of power reduction because of this shadow impact. So the point is doing the pre-feasibility study before this makes a big difference in terms of the power performance. So there is a question like, will all these people do this before installing solar? The question is a $1 billion question, because in spite of having many dealers, vendors who does that, but unfortunately, only few people have a technical expertise to analyze in detail to understand whether installing solar here will make sense or there makes sense, or what's the kind of the site azimuth is being displaced, and whether the south is true north or true south, and what are the kind of environmental conditions there, and how frequent the dust accumulation happens there, and if the site is near to the seashore, or if there is a site near to any oil refinery or something, because everything matters. If it is a dump yard, then there is a higher possibility of the chemical deposition over the surface. If it is near to the shore, then the higher possibility of the salt mist precipitation effects over the frames, and also the glass surface. So everything needs to be taken into control and consideration before ever going into the design and implementation of the system. So the moment when we go for the green hydrogen production, we need to know exactly where the factory is going to be set up, and what are the environmental and climatic condition, and what is the adjacent building nature of the particular location. If the building is separate and alone and islanded, then it's just a matter of fact to implement it. But if it has been very congested, or maybe adjacent with a lot of tall buildings, or if it is very near to the seashore or something like that, then this is something which needs to be taken care much more in terms of the uh, so that the 3D rooftop or the 3D ground mounted systems can be done, and the result will give you the exact energy performance. So here we can see the analysis reports which we extracted. Whatever we have done is all before the installation. So these are all we call it as a pre-feasibility study. So pre-installation, that's a feasibility study. So in the feasibility study, we will evaluate, in case if I'm going to use this many numbers of solar panels and placed at this much of tilt angle and deviated at this much of azimuth with this much of inverter, how much amount of energy I can able to generate. So basically you have a scope to change your panel, change your inverter, change your tilt angle, change your orientation, and can figure it out what is the best design, what is the best possible optimal design that you can able to adopt there, so that the system can able to produce a maximum of power output. So the idea of putting any system is to get the maximum output. So if you want to get a maximum output, then we need to figure it out the optimal point of parameters. So if you want to figure it out, then we need to do all this homework well in place in advance to make sure the system is designed perfectly so that we can able to have be able to reap out the maximum yield out of the system. So the project timeline will be vary according to the project, right? From the customer, approval, then getting the approvals from the Tangitco or whatever the discoms, then material dispatch, civil works, panel installation, then getting the approvals for meter, net feeding mechanism, and all the other factors. So now I just want to throw a quick question, like you all from the academic background, like how many of your institution is having solar installed at your campus? So now there'll be a question of where this solar, whatever we are discussing, will be connected. So basically, the solar will be connected here. I'll show you. So this is your main transformer and this is your rectifier. So basically, it is going to be connected in between. So let me put one um, whiteboard for you to make understand very clearly. You can able to see the white screen?
Yes, sir. Yes, sir. If it is visible, sir.
Okay. So basically, there is a grid setup. Okay. So 1 minute, I'll put it other way. So this is your existing grid. Who is writing? I request others not to write on this. So let me explain. So this is your grid. Okay. So basically, the grid supply is a three-phase supply. So the supply is coming to your yard. From the yard, it's coming to your substation. From the substation, it is coming to your power room. From the power room, it will go to your distribution points. From the distribution points, the loads are connected. Okay. So basically, electrolyzers are going to be connected here. Okay. This can be one electrolyzer, this can be other electrolyzer. Now, where the solar will be implemented? That's the next question, correct? So, solar will come basically before the main distributions in the power room. So, basically, the power room has the main busbar panels. So, solar setup will have the DC which is produced and that comes to the inverter. So, the inverter will convert DC to AC and that AC will come here and it is connected on the main bus bar itself. So the concept is whatever power produced during the daytime, okay, so that will first utilized by the loads. In case there is no load, then instead of coming this way, this power will go to the grid. It will go to the grid. So generally we have a energy meter which is kept at the entry of power room. So this is your energy meter. So this energy meter is going to be replaced with a solar net meter. Okay. So the moment it is going to be replaced with the solar net meter, the advantage is we can able to account how much of energy being imported from the grid and also exported to the grid. So imported and exported both is recorded in this meter. Okay. So that's an advantage. Now, if we have any excess that is recorded separately, if we have any import that is recorded separately. But we have designed the system in such a way that maximum amount of power is going to be utilized in the daytime itself, which means the possibility of export is going to be negligible. Okay. So the possibility of going to be export is going to be negligible. Now, in case if solar is not performing, what will happen? Regularly, conventionally, whatever the power taken from the grid will be going to the load. Okay. So the point is, in case if the load requirement is 100 kilowatt and the solar which has been operating at the rooftop is producing 50 kilowatt, then what will happen? This 50 kilowatt will first come to the load and the deficit is now 50. So that 50 will be only taken from the grid. So here the meter will record only the 50, but actual consumption is 100. Whereas the savings of 50 is being supported by the solar. So this is how solar will work. So in case if our day demand is more, then definitely it's not only for integrating renewable into green hydrogen production. It is for each and everybody. It is irrespective. It can be a college, it can be a you know office or factory. Whoever operating during the daytime is better to put solar, no doubt about it. So, any doubts in this methodology of how system works?
No, sir.
Uh, Yeah, so I got a question in the chat from Dr. A.S. Vinci. So I would like to answer this question. It is a good idea to install solar for home usage as the power usage is minimum during daytime. That's why I clearly told for residential consumers, you have the possibility of net metering. So in net metering, what happens is, so I'll explain the concept of net metering. So you have a solar rooftop, it comes to the inverter, and this is your grid, this is your energy meter, and this is a distribution point, and it is coming to your load house. Okay. Now, how net meter works is if during the day, if there is 10 units produced and it is coming to this point,
but during the day you have only consumption of 3 units at the home because you went for the office. So the surplus of 7 units will be get exported in the grid. So basically this meter have an export credit of 7. And you're coming in the evening, 6 o'clock or 7 o'clock, by that the solar is not working. And you're switching on the other two AC where the consumption is going high and it is consuming the 7 units for the next 5 hours per se. For this 7 units, it is going to be taken from the grid, but it is not going to be charged because you already sent the 7 and the 7 will adjust this 7. So that's a unit to unit adjustment, and it makes a sense for installing solar. Even if you're not using during the day, still you can able to adjust the power production happen during the day. So for residential, it is really a good idea to go for solar. And also government is giving 78,000 subsidy for you guys. So you can able to avail that 78,000 as a subsidy benefit. So any other doubts?
No, sir. Participants, if you have any doubt or clarification, kindly post it in the chat box. Dear professors, if you have any queries, kindly post it in the chat box.
Sir,
Yeah.
good evening, sir.
Good evening.
Sir, it is very good concept that green hydrogen that we are integrating with the solar and hydrogen production, that is solar hydrogen production. Thing is, the cost of electrolyzers, whether it is PEM or alkaline, it will be much more higher, plus the cost of solar panels. And we need a pure water for electrolysis process. And what about the durability and degradation, which involves a complex process, right, sir? So, for example, I want to produce this, I'm only talking with the case study like 14 liters or 1 liter of hydrogen. How much will be the cost, sir? Which is it affordable for a commoner?
No, not at all. That's why installing, it's not like solar. Now for 2 kilowatt, 3 kilowatt, a consumer can able to, a residential consumer can buy, can afford now.
Yes, sir.
You can get the system in 1.5 lakh, 2 lakh. But green hydrogen is a green hydrogen system. I mean, especially the hydrogen electrolyzer system. Minimum, you should go with at least a 25 kilowatt system for a better realization. And but economically, if you see, at least 200 kilowatt electrolyzer size will only make the hydrogen to be a sellable point of view in terms of the pricing. But the realization point of view, it starts from 25 kilowatt, 50 kilowatt. That should be the minimum capacity for someone to understand the costings and economics. If it is much less, then it's definitely and very, very expensive and also very challenging for you to store the hydrogen, handle the hydrogen, and also maintain safety at a normal place.
Sorry for the disturbance, sir. Please kindly
No
proceed, sir.
problem. Thank you. Any other doubts?
Yes, sir. One second, sir. Dr. Revati Duraivilu, please kindly unmute your mic, then ask your queries. Revati Duraivilu, ma'am.
Yeah. If a solar installation reaches significant percentage of adoption and there are any ongoing research efforts to address the issues related to land filling solar panels and land use challenges arising from it. Land filling means you mean the disposal of solar panels?
Disposal of solar panels, sir.
Okay, see, there is a process involved. We cannot just landfill it. The recycling policy of solar panel clearly states the manufacturer owes the responsibility of bringing back the panel, putting into a recycling process, separating the aluminum frames, glass particles, EVA films, silica separately into a microgranules, and that is sent for the recycling process. Finally, the plastic component is separated, metal components are separated, silica is separated, and that is used for the further application. So we can't simply dump it, then it has become a soil pollution.
Yes, sir. Sir, how it is possible, the lifetime of solar panel is 25 years, whether the company is responsible for that, maybe company is closed,
See, I'll
how
tell
it can be?
you, if you are installing solar today, for large scale system, you will be recovering in 7 years or 8 years, the investment made. Post
Okay.
that, you will be making only the profits. Okay. After making the profit also, if you want to shut down the plant, then after 20 years, even now there are companies who do the recycling of solar. After 15, 20 years, the scope and the nature of recycling companies plays a big role. There will be a big demand for recycling sources. I mean, recycling of the raw material which is required for recycling, especially from solar. There are many solar recycle plants which has been set up now also. So those companies are very interested to take your panel even at a cost, at a scrap rate, and that's going to be revenue for the supplier in a way.
Okay, sir. Thank you, sir.
Yeah, thank you. Any other doubts?
Once again, sir.
Participants, you can raise your queries.
Sir, good evening, sir. Myself, Karthikeyan.
Yes.
So we have installed a 100 kilowatt capacity panel in our campus.
Hmm.
But ever since installation, especially during the last 6 months or so, we have been regularly paying some penalty to the electricity because of the power quality and associated issues, sir.
Hmm.
What could be done to rectify that issue?
Where is the plant?
In our college, sir, the host institution, Krishnasamy College itself is having a rooftop plant having a capacity of 100 kilowatt. Every month, EB levies us some penalty because of the poor power quality getting supplied from the grid to the supplied to the grid from the panel.
See, this is going to be a hypothetical debate. Why? Because there should be a study or evidence that needs to be arrived that this inverter is the culprit. Okay.
Okay.
Do you made any study or any conclusion that this inverter is the culprit which creates that harmonics?
No, sir. People are telling that either we have to go for that zero.
People are telling that exactly. See, the
yeah,
concept of solar inverter is it works in parallel with the grid. Okay. And the inverter, whatever the on-grid inverter which comes into the market, getting the BIS certification and getting the IEC approvals is not supposed to inject not more than 3% of the total harmonic distortions into the grid. Okay. So in case if the total harmonic distortion is going more, the inverter is not supposed to work. Okay. So it's very evident and clear that the solar inverter will never create harmonics. But the nature of supply is like that. And that time when the power is being injected, it might create the supraharmonics or whatever the other effects that we can able to face in the grid. So technically, one has to did a detailed energy audit well in advance before even installing solar to estimate whether the existing grid is having a problem like this. Did they did any detailed energy audit well in advance to understand whether this kind of harmonics or power factor issues is already available in place?
I think no, sir. But the what the internal power team and also in consultation with the electricity people and the supplier, they concluded a zero export device need to be installed in place so that the issue can be resolved, or a kind of power regulatory system like a variable capacitor kind of a thing can be installed to resolve the issue. But because of our lack of knowledge, we couldn't intervene into that and tell that. Through this program, I wanted to get your insight on that so that we shall be able to analyze further.
Sure, I'll tell you. If you install an 100 kilowatt rooftop solar, have you got your energy meter get replaced with a net meter?
Yes, sir.
So the meter, the HT meter, you have changed into net meter.
Yes, sir.
Okay. So in case if you already replaced your energy meter with net meter, there is no requirement of installing a zero export.
Okay.
Because the moment when you start interacting with the grid, then the possibility of harmonics might be possible. Correct?
Okay.
You cannot control the export of energy because there is no evidence that only your solar is being filtered and the grid is available. Correct?
Yes, sir.
So technically that is ruled out. Now
Okay.
coming to the next point, what is the next statement you told?
They had spoke about some power factor regulator setup like a capacitor bank or so to be installed.
For that, you need to do a detailed energy audit in
Okay.
your campus
Okay.
to figure it out what are the main components which is under problem to create such kind of a power factor drop. Okay. It can be your AC compressors, it can be your pump, it can be your any induced fans, it can be your centralized air conditioners, or it can be your old fans. So there are
So
multiple factors and reasons
my
that you might face this situation.
my doubt is, sir, earlier without this solar system, before 6 months, we never faced this issue. Only after installation of the solar, we have started facing. And will there be a possibility that poor quality of power getting supplied to the grid or so, or for that reason they might penalize us? This is how I got information from the AE.
See, to conclude this point, I need to see your electricity bill copy to know for what purpose they put the penalty. It is for the power factor penalty or maximum demand, or is there any network charges have been leaved off? On what head the penalty has been raised?
We will get back to you on this, sir. We shall be glad to take your guidance on this. Thank you, sir. Thank you very kind.
Yeah, I think you all got my mobile number and email ID, right?
Yes, sir. Yes, sir.
Yeah, so you can connect me personally. I could able to support you on that.
Thank you, sir. Thank you, sir. Good day.
Thank you. Thank you very much. Is there any other doubts from the team?
Thank you, sir. Thank you for your thoughtful presentation.
Thank you. Thank you.
Kindly, all the participants and speakers, sir, please turn on your camera, sir. We need to take a screenshot.
Okay.
Dear participants, kindly unmute your camera.
It has been enabled. Participants, kindly turn on your cameras.
Dear participants, please unmute your camera. Now, if it is enabled, Rajaganesh sir, please unmute your camera.
I'm already.
Okay, sir. Thank you.
Where the structures of stamen and pistil. Yeah. இத்தனை இருக்குல்ல.
Screenshot எடுத்துட்டீங்க. எனக்கு எடுக்க வரல மேம். One second. Hold on one second. Thank you, dear participants. Good evening to all. On behalf of the organizing committee of the Atal sponsored faculty development program, I extend my sincere and heartfelt thanks to distinguished resource person, Engineer Rajaganesh, Director, VATIO Industrial Energy Private Limited, Chennai, for delivering an insightful and industry-oriented session in the Day 3, Session 5. His expert sharing of real-time industrial practice, emerging technology trends, and practical perspective has greatly enriched the knowledge of all participants and effectively bridged the gap between academia and industry. The session was highly engaging and provided valuable takeaways for teaching, research, and professional development. We also express our gratitude to the AECT Atal Academy for their continuous support, and we thanks to the all participants and today's resource person for the active involvement, cooperation, which made this session a success. Once again, we thanks to Engineer Rajaganesh for his time, dedication, and valuable contribution. We look forward to the continuous academy industry collaboration in future. Thank you, sir. Thank you with us. Thank you so much, sir. Thank you, Rajaganesan, sir.
Thank you. Thank you, sir. Thank you very much for your note. And also, I thank very much for all the participants who was very attentive. And it's 171 participants who's sitting by 7:30 is a real big task, and it is happening. And I think in the short span of time, in 1.5 hours, how much I can able to compress and deliver. I have tried it my level best. And this subject and field is something which is very big, and there is a lot of scope to work on it, to find the problem statements and come up with a lot of solutions. And I definitely hope the participants will work on that particular field and come up with some innovations and inventions. All the very best to you all. Thank you very much. Thanks for the opportunity.
Thank you, sir. We are sure
Thank
about
you.
it. Other participants will make their research very innovative and useful for the society, sir. Thank you.
Yeah. Thank you. Thank you very much.
Thank you, sir.
Thank you, Rajaganesan, sir. Thank you very much.
Thank you.
Dear participants, please stay in the call. The next resource person is arrived.
Sir,
Now,
Hariharan sir, are you online, sir? Hariharan sir? Hello? Sir, mic disable பண்ணிட்டீங்களா? Unmute பண்ண சொல்றாரு.
Hello.
Yes, sir. Are you online,
Can I
sir?
hear you?
Yes, sir. You're audible.
Okay.
Okay,
Is
just
it
a minute,
loud and
sir.
clear, right?
Yes, sir. Just a
Okay.
minute. I take immense pleasure in introducing our resource person. Hariharasuthan Tamilchelvam is a power system engineer with over 15 years of experience in electrical engineering field. He holds BE in electrical engineering from EGS Pillai and MBA from power management from UPES. Now, he is currently working with Alstom Transportation Saudi Arabia, specializing in power systems for metro rail projects. He has previously worked with Powerflow and JTech, gaining practical experience in protection engineering, testing, commissioning, and power system studies. He has approved protection engineer with Saudi Arabia Electricity Company SEC and National Grid Saudi Arabia, and he is an active member in Institution of Engineers India and Society of Power Engineers. He has a very great contribution towards the society. His expertise lies in power system protection, grid coordination, and large infrastructure products. We welcome you, sir. Now it's time for handing over the session to Harihara, sir. Sir, please kindly proceed with your session, sir.
Thank you. Thank you so much, ma'am, for a wonderful introduction. Let me share my screen.
Yes, sir.
I hope you can see all my screen, right?
Yes, sir. It's
yes,
visible.
sir.
Thank you. Thank you so much. Yeah. Good evening to all. Uh, Thank you so much, ma'am, Dr. Sikalevoni, ma'am. Thank you so much for your welcome. It's a very pleasure to be part of this faculty development program. And I sincerely thank this organizing department and especially ma'am, Dr. Sikalevoni, ma'am, for trusting me to bringing me in this program and this opportunity as well. Let's go to the sessions.
Thank you,
Today's
sir.
sessions focuses on welcome. Yeah, today's sessions focuses on hydrogen energy and digital twin applications from an industry-oriented power and railway system perspective. As you all know, the hydrogen is emerging as a clean energy carrier, while digital twin technology enables free-time modeling and monitoring and optimization of the such complex energy systems. So that this is a very future upcoming technologies. Through this session, I aim to connect theoretical concepts with the practical industry applications, highlighting their relevance to the power grid and railway traction systems. Let me briefly introduce myself, since Dr. Kalaivani ma'am already explained me about myself, even though I just wanted to brush up my introduction. I'm an electrical engineer. I also hold an MBA in power management. Professionally, I have 15 years of experience. I have been working as a power supply engineer with a hands-on experience in power system engineering, railway, and metro electrifications, traction power systems, and testing and commissioning as well. Alongside my core engineering work, I have done my write-ups in power flow studies, for anti-effect studies and surge impedance loadings as well. Let us begin by understanding why these technologies are critically important today. It's a very important question. Why now? First, there is a global push towards the decarbonization. Governments and industries are under pressure to reduce the carbon emissions due to the climate crisis. Second one, the energy sources like solar and wind are intermittent. They don't generate power consistently, which creates the grid challenges as well, right? And the power and the transportation infrastructures was not originally designed for such high renewable penetration. So there is an intermittency. So, and the fourth one is there is a rising demand, not just for the electricity, but for the sustainable mobility, especially in railways and metros. And finally, you can see that digitalization and the smart operation are becoming a mandatory to manage the complexity, reliability, and safety. So overall, the hydrogen combined with the digital twin technology directly addresses all these technology challenges. So here we consider as a hydrogen as an energy carrier. As you all know how the hydrogen is produced and everything. So we just go to the hydrogen as energy carrier. Hydrogen is not primary energy source like coal or solar. It is an energy carrier. That means the hydrogen stores energy and delivers it when it is required. When hydrogen is used as a fuel cell, it produces the electricity, heat, and only byproduct is the water. From the environmental perspective, this is extremely important. Zero carbon emissions at the point of use. So this makes hydrogen highly suitable for the power system, railways, heavy transport, and industrial applications. And why hydrogen? We means it's infinite supply. And as we discussed, there is no carbon footprint here, easily transported, and high energy density. Produces the clean power from the green hydrogen. It can be stored for large quantities and the long periods. What are the type of hydrogen productions? Hydrogen does not exist freely in nature in large quantities. It must be produced from components like water or hydrocarbons. The production method defines its environment impact. By the way, we have the different type of hydrogens: gray hydrogen, blue hydrogen, green, yellow, and pink hydrogens. The gray hydrogen produced from the fossil fuels, but it emits the CO2, carbon. But the blue one, the fossil fuels, it's also be generated through the SMR and the carbon capture and the fossil fuels, and the carbon CO2 can be captured in this hydrogen. So after carbon captured, the hydrogen becomes blue. We like it's not becomes blue. We named as a blue. And the green hydrogen produced using renewable electricity. And the yellow hydrogen, it's also from the renewable energy, but from the solar power specifically. So these are the hydrogen types. From the power engineer's perspective, green hydrogen is the most important because it's directly links with the renewables, with the storage and the transport. Let's go to some basics. What is an electrolyzer? The electrolyzer is the heart of the green hydrogen production. As you can see in the diagram, the pure water fed into the electrolyzer and a DC electric current is applied. When you apply the DC current to the electrolyzer and the cathode, hydrogen gas is produced. At the anode, the oxygen gas is released. So these are how the electrolyzer can produce the hydrogen. The hydrogen is then collected, compressed, stored, or directly used as a fuel. And electrolyzer is in a power sector side or the electrical engineering point of view, we could see the electrolyzer is a large controllable DC load when we connected with the power grid. And also the electrolyzer acts as a interface between the electricity and hydrogen. These are the type of electrolyzers. There are three main electrolyzer technologies: alkaline electrolyzers, PEM electrolyzers, and solid oxide electrolyzers. The PEM technology is a modern and compact and very fast responses and suitable for the solar, wind, any renewable energies, and the cons is the higher cost. The alkaline is a very usual one and the oldest, most proven type of electrolyzer, which is in running now in all the industries. Low cost and long life, but it's a slow responses, not ideal for fluctuating renewables like power grids. And the solid oxide electrolyzer is a high temperature electrolysis. Solid ceramic materials type of material have been used in this electrolyzer. It's a very high efficiency, usual in industrial settings. Still under development it is. And for the power sector, we always consider power sector and the railways, the PEM electrolyzer was the most suitable type. And here is some comparison between the electrolyzers. There is what are the electrolyte, the temperature, efficiency, and the pressure bore, and voltage response time. Among all these comparisons, you could see physically the PEM is the most suitable from the power sector point of view. Maybe the alkaline and the SOE could use some other applications, but the PEM is most suitable for our power sector. As you can see here, the response time in the PEM, it's a milliseconds. This is very much needed in the frequency stabilization, grid stabilization topics. So that is why we called the PEM is a very suitable for power grid applications. Hydrogen storage and the transportation. And it explains how hydrogen is stored and transported, which is critical for practical hydrogen deployment. On the left, as you could see, there is a flow diagram. The hydrogen storage is classified into physical phased and material based, such as physical based is a compressed gas, cold compressed, and liquid hydrogens, which are commercially available but energy intensive. It also shows some material based storage like metal hydrides and the chemical carriers, which offer a higher safety and density but are still emerging there. And the pipelines transport, there are, if you consider the physical based transportations, it has the pipeline transport tube trailers. The pipelines for large scale continuous supply. It's an efficient overshot for the medium distances and require dedicated hydrogen pipelines. And the tube trailers, compressed hydrogen has transported in high pressure cylinders. Even the compressed, this tube we have multiple types of tubes, type 1, type 2, type 3, and type 4 and all. Even it's flexible and suitable for the small to medium volumes. Apart from this transportation, even hydrogen can be produced on site. That is electrolyzer based. Hydrogen produced directly at the consumption of sites, so it eliminates the transportation cost and losses. And it doesn't require any centralized hydrogen production. Let's comes to the hydrogen grid introduction. How hydrogen integrating with the grid. So as you can see, the grid stability, the renewable like wind and solar are clean, but they are also intermittent. So normally in grid stability, we call it is too little or too much. This is a grid story. We simply say that. What is too much? When there is too much of electricity, what can we do? How the power system will respond? When there is too little of electricity, how the demand meets. So that's why here the hydrogen will play the major role. When there is a too much of electricity, electrolyzer ramp up and absorb the surplus. When there is a too little electricity, the electrolyzers pause instantaneously and it produce the electricity from hydrogen. As I told you before, electrolyzer is a large DC controllable load. And here we can understand the electrolyzer is not just a hydrogen producer, but a smart and controllable electrical load. It plays a crucial role in the grid stability. As you can see this diagram, the electrolyzer is connected to the power system through the AC/DC converters, grid stimulators, and the H2 SCADA system. This setup allows real-time monitoring and control based on the grid conditions, power flow, and the signal flow are connected with the system, so the electrolyzer can respond dynamically. During this period of high renewable generations, such as a strong solar or wind output, the electrolyzer ramps up and absorbs the excess electricity, preventing the renewable curtailment. When grid demand increases or the system becomes stressed, it can be ramped down instantly, freeing capacity of critical loads. The flexible operation provides the grid support and the demand responses, helping balancing the supply and demand. And overall, the electrolyzers act as a smart stabilizing assets. It can convert the surplus renewable energy into the hydrogen while strengthening grid reliability. So the grid stability is the most complex system in the power system. So which is this hydrogen electrolyzer, which is helping a lot to make a grid stability in this. As I told you before, the PEM type of electrolyzer, it suits a more suitable method for the power system. Why it is? As I told you, the fast response, the working principle of the grid advantage of the PEM electrolyzer, as you can see in the diagram, it is very easily we can understand from this. The DC power is supplied across the anode and the cathode and separated by the proton exchange membrane. That is the name itself. We call it a PEM electrolyzer. The protons pass through the membrane while the electrons flow through the external circuit. It's a very basics how the working principle of this electrolyzer. Okay, from the power sector view, the PEM electrolyzer provides a sub-second response. It's a fast response time and high efficiency at the partial loads. And compact and modular, it easy to scale and deploy the near renewable plants or in urban spaces. And their compatibility with the power electronics, SCADA, and enables the demand responses of frequency support and the peak savings, strengthening the grid stability. If you have any doubt, you can stop me anytime. Okay.
Sure, sir.
Okay, thank you. Okay, let's go to the topic. It's a power to hydrogen. Let's say if we talked about the grid stability, there is a two-way, power to hydrogen, hydrogen to power. So let's first discuss about the power to hydrogen when it's absorbing the excess renewable energy. The excess power from the solar and wind generation, typically during the low demand or consumption periods, it's diverted to the electrolyzers instead of being curtailed. And the power to hydrogen provides active power balancing, reduces the renewable curtailment, and supports the sector coupling by allowing the hydrogen to be used across the power, transport, and all the other industries. It also enables decentralized productions. It can be integrated with the renewable sites and reducing the transmission losses. The stored hydrogen can later be used in rail traction and industrial processes and reconverted the electricity during the peak demand periods, improving overall system flexibility and reliability. Here it's a hydrogen to power. As you can see in the diagram, the electrical grid. From the grid, the power, that is a dedicated transformer which is deployed for the electrolyzer, which is stepping down the voltage, and there is a one converter is should be there, but it is not included in the diagram. That is a converter. It should be converted from the AC to DC, and feed the DC supply to the electrolyzer. From the electrolyzer, the hydrogen is produced and is stored. From the stored hydrogen, it's using back to the fuel as work as a fuel cell. From the fuel cell to we regenerate the power from the hydrogen, and we supply to the grid. As a fuel cell produces electricity by combining hydrogen and oxygen, it generates the power by splitting the hydrogen into the protons and electrons. You know, the hydrogen to normally we used to say H2P, hydrogen to power, enables the dispatchable generations, allowing the hydrogen act as a long duration energy storages. And also, it forms a closed loop energy storage system with support of high renewable penetration. It's a closed loop. Why? Because we generate from the grid, from grid to again back to grid. So it's a closed loop energy storage system. The hydrogen storage, medium and long duration energy storage. Why hydrogen plays a crucial role in the medium and long duration energy storage, especially in the renewable rich power systems. And the renewable energy from the wind and solar is converted into hydrogen and stored for the later use in fuel cell, and transportation, and industrial processes. In comparison, the batteries are high efficient for short-term energy and balancing the fast responses, such as a frequency regulations and a ramping support. Hydrogen, on the other hand, it is better suited for the large scale and the long duration storage, enabling the sector coupling between the power, transport, industries. This makes it particularly valuable for seasonal storage and the backup power applications, including the round trip energy losses, as I told you before. In the infrastructure and the safety requirements, such as high pressure tanks and the pipelines, it's a high capex. So, and as you can see, the hydrogen storage, you know, there are a lot of complex and challenges for the storage and transporting the hydrogen, compressed hydrogens. So here, the digital twin and the optimization tools plays a crucial role by improving system design and operational efficiency and the predictive maintenance and making hydrogen storage technically. All these challenges we can come through the digital twin technologies. Yeah. And hybrid hydrogen and battery systems. As of now, we have discussed the battery hydrogen alone system. Now, the hydrogen plus the battery, we call it as hybrid hydrogen. This is important for modern power and transport applications. The batteries are highly effective for short-term fluctuations, operating from the seconds to minutes, while hydrogen systems cover longer durations, from hours to days, especially during the renewable energy shortfalls, combining both improves grid stability, reliability, and asset utilizations across the multiple time scales. Why hybrid? The batteries handle the short-term fluctuations. It covers the longer duration. In the practical use, the batteries manage the fast power variations, while the hydrogen stores the excess energy for the later use. The approach is very ideal for the renewable energy smoothing of grid systems. The benefits from why we have the hybrid hydrogen and the battery system. The benefits is it's all focusing on the grid stability. The grid stability is a very important topic in this power sector. So that's why we always talking about the grid stability. The improved grid stability and the energy reliability. The better asset utilizations across the different time scales. And this can be used as a renewable energy smoothing and off-grid or remote power systems and rail and mobility. Batteries manage the rapid changes, and hydrogen stores access for the latest. Okay. However, the successful deployment needs smart control strategies and the cost optimization and the careful efficiency of trade-offs. Here is a hybrid hydrogen and battery systems control strategy. The control strategy for the hybrid hydrogen and the battery energy system coordinated through the energy management system or EMS. As you all can see, the multiple power sources, solar, wind, and the main grid, all feed to the system, feed to the grid. Okay, the EMS means energy management systems, continuously monitoring the system conditions and issues control commands to both battery energy storage system and the hydrogen storage system, which includes the electrolyzer, hydrogen tank, and the fuel cell. The EMS decide when to draw the power from the battery and when to dispatch the fuel cell. It's ensuring the energy use, extended battery life, and optimal fuel cell operations. And during the regenerative braking or surplus renewable generation, what is that regenerative braking energy? The regenerative braking norm we used to call in the railway systems. Regenerative braking is a big concept in the railway systems. Whenever, for example, in a track, you have a two track. There are two trains running parallelly with the two individual alone tracks. When the braking, we have the lot of dynamic braking and plugging method of brakings and the regenerative brakings. The regenerative braking, which means it's converts the energy when the train brakes, that energy converts back to the electricity. So we use it that, we feed the power to the trains, electrical trains, and the trains runs and that it traction. So it grows the track. When the station is approaching, the trains docking at the station, of course, we apply the brake. That brake, when the speeds slowly reduce to the stations, that braking energy converts as electricity. That is what we call it regenerative braking energy. Okay, the regenerative braking energy is stored in the battery. Normally, we in the metro system, so we use it as some utility supplies, or the regenerative braking energy is sharing with the other train which is in the same zone of electrical, where the train is parallelly contributing the same power zone. So it transfers the energy between the trains. If there is no train, it will be utilized in the station itself for the utility purposes. And also the another method is the regenerative braking is stored in the battery. So during regenerative braking or surplus renewable generation, the energy is the first stored in the battery for the fast responses. When the battery state of charge is very low or during the sustained demand, the fuel cell recharges the battery, especially in low load periods. There is operationally the system works in three methods like ideal or startup. Like it's this operational modes for the uh, metro systems. I'm talking about the metro systems. The ideal for the startup, where there is a battery supplies the power. So when you wake up the train, so we need the battery provides the power to the train to wake up and runs into the track. When it starts cruising or traction, the fuel cell in the main source and battery supports when needed. High demand means both fuel cell and battery operate together. Let's see after slides, we can discuss detail. It's just a method how the hybrid hydrogen and battery systems works on the metro systems. Let's comes to hydrogen energy to the railway system. How hydrogen energy we are utilizing in railway systems. It's a example of a hydrogen train. The architecture and the working principle of the hydrogen powered train. Here I'm going to explain, just discussing with you. The hydrogen storage cylinders are safely mounted on the train roof. As you can see, the parts, hydrogen storage cylinders and cooling fans, compressor, and the battery or supercapacitor. Normally, we call as a supercapacitor as here. The motor blowers and the three-phase AC motor on the bogie sides. And the power sides, we have the DC link and the main inverters and three-phase AC motors and the auxiliary inverters. Okay. So the hydrogen storage cylinders are safely mounted on the train roof. Hydrogen from these tanks is supplied to the PEM fuel cell slab, where it is converted into the electricity and producing, as you know, only the water as a byproduct. The electrical output from the fuel cell is regulated through the DC link and the power electronic converters. Normally, we call it as a high-speed circuit breakers, HSCBs, the very, very high-speed operated circuit breakers, which is called as a DC link. It's including this complete power module, including the inverters and the rectifiers. A battery or supercapacitor, it is connected to the DC link to handle the transient power demands. Whenever there is no power, it can generate. So such as acceleration and to capture the regenerative braking energy during the acceleration, as I told you. The processed electrical power is then fed into the three-phase AC traction motor. We have main converters and main inverters where we can step down the AC voltage, or we can convert from DC to AC and use for the train lights and the train brakes and all other utilities in the trains. So the auxiliary systems such as the cooling fans, compressors, and the onboard loads such are supplied by the auxiliary converters. That also I told you. The auxiliary converters can able to convert from DC to AC and step down that AC voltage to 110 volt to 24 volt. There is a lot of subdivisions voltage which can able to feed the supply to the auxiliary system of the train. And overall, this configuration, it combines fuel cells for the continuous cruising power, traction power, and the batteries for the dynamic load support. I hope you all hear my.
Yes, sir.
Hello.
You're audible,
Yeah.
sir.
Okay. In case of any doubt, you can stop me at any time. we can
Sure,
discuss.
sir, sure.
Okay. Let's go to the electrified railway. That is a 25K. That is, in the metro railways, yeah, we have overhead line like 25 kV AC, which is mostly commonly available in India. There is 750-volt DC third rail system, which is available in Saudi Arabia here. So here we'll talk about the electrified railway so as a 25 kV. It explains, how hydrogen system integrate with the conventional 25 kV AC supply electrified railways. You know, the green electricity, normally we call it as a green electricity from the renewable sources. It's as all, since we discussed this a lot about the electrolysis and electrolyzers, so it produces the green electricity. So the green electricity used for the electrolysis at the depot level, as I told you, the electrolyzers we don't need to use as a centralized hydrogen production. So we can use one electrolyzer setup at the depot level to hydrogen production and some station level hydrogen productions as well. So it's used for the enabling the hydrogen production and fast fueling, right? So hydrogen trains operate at non-electrified section. There is no need of third rail systems. There is no need of overhead transmission lines, which is carrying 25 kV systems. It doesn't need any without any overhead lines. So we can run this train with the non-electrified sections. So from the railway's view, the electrolyzers act as a controllable loads. It's a DC load, absorbing the excess grid power. This excess grid power, where it is come from? From the regenerative braking. So during the peak demand or grid stress, so the fuel cell can supply the power back to the grid. So the here we had, the grid traction and hydrogen electrolyzers can help balance the grid by adjusting the hydrogen production, and the fuel cell can supply the power back to the grid, as I told you before. There is a lot of some points that we have to conclude it. The hybrid deployment possibilities, energy supply integrations, load management, and grid support. These are the key features by using the hydrogen system in the metro side.
Excuse me, sir.
Yeah.
Is this will be a grid connected system or a standalone system, sir? It will be.
It's not a grid connected. It's a standalone. That's what we call this electrolyzers is a decentralized production, hydrogen production. So, for example, you have a one area from this location A to location B. You have to try run the train. There is no grid, there is no power supply. So normally in those areas, the ancient days, the diesel engine trains can use it for uh, those areas, right? But now we are using the green energy. Like we install the electrolyzers at the location A and the location B. We can refueling the stations when the train approaching the stations, or else the coming slides, so you can see that our Alstom's hydrogen train, which is carries the uh, hydrogen cells and cylinders with the train itself to generate the power. So it's completely standalone. There is no grid needed at all.
Okay, okay, sir.
So,
It's
yeah.
being a large scale hydrogen storage solution, no, sir. We need a large scale hydrogen storage solution for this, no, sir. How do we go
Come,
about it?
come again.
Being a standalone system,
Yeah.
we need large scale hydrogen storage, right? Then how do we
Yeah.
solve those problems, storage problems, I'm asking?
Yes, if it is a standalone, like the hydrogen, for example, we loaded some hydrogen cylinders on the train, and we know that how long it can be sustained for the and providing the traction to the metro, right? Meanwhile, we can in meanwhile stations we can install the electrolyzers to generate the hydrogen production to refueling the metro trains. Since it's a battery, which means it's a very short time durations, and the hydrogen is a long durations, right? So we can use it from stored hydrogen as a fuel cell. We can generate back to electricity and feed the, and also you can see the train is having the hydrogen fuel cells and batteries together in the train. So the hydrogen fuel cells can generate the electricity. That electricity can charge the batteries, and the batteries can support the tractions. The battery itself has some uh, durability, and also the hydrogen fuel cells has some durability. So you can convert back from the like from battery hydrogen to battery to charge the batteries to track the
Yes, sir.
enable the traction the train. That's why we have the depot level hydrogen protection and station level hydrogen protection we have. You know, in the depot level we have the number of trains, so we can generate. We don't need to get the power supply from the grid. We can generate the power from the hydrogen when we install the electrolyzer at the depot level. I hope you can.
Yes, sir.
I
Please
answered you.
proceed, sir.
Yeah.
Okay, sir.
Okay. Thank you. Thank you for the good introduction. It's good to being interact. Okay. Yeah. Here is example of our Alstom's own hydrogen train. Its name is a Radio Island. So Radio Island, it's a world first commercial hydrogen train. It's developed by Alstom company. It's a zero emissions alternative for diesel trains. And one minute, as you can see, the above over the roof there is a hydrogen storage cylinders which is installed. Same it is here. You can see. Can I navigate it? Okay. As you can see, the over the roof, there are the hydrogen cylinders are placed there. It's a so the powered by the hydrogen fuel cells and batteries to generate the electricity for this traction. It's combined. It's a standalone. There is no need of grid as ma'am has requested. So the power, it is powered by the hydrogen fuel cells and the batteries to generate the electricity for the tractions. No need the overhead lines, and top speed you can see the 140-kilometer range. Normally, the urban area, 80-kilometer or 90-kilometer is the maximum allowed for it is a standard. But even though the train can reach 140-kilometer per hour, and there is no emissions, it's zero emissions and the clean water vapor only. There is no CO2, there is no NOx and participate pollutions. The key advantages and the impact of the future outlook. You know, it decarbonizes the rail without the need for the expensive electrifications. And again, you can see the hydrogen and the fuel cells where it is placed, and where the auxiliary converter is placed, and the lithium-ion batteries. How the hybrid system, hydrogen and lithium batteries, can help this train to traction on the full tractions. And here you can see this. Here it is the hydrogen cylinders or hydrogen fuel cells are placed over the roof. It decarbonizes the rail without the need for the expensive electrifications. Performs like the diesel, but with the lower noise that is and smoother operations, and enables the digital twins use of the real-time monitoring efficiency and maintenance. And it gives the way for the clean and sustainable rail mobility. And also some information about our own Alstom's hydrogen train in India and Saudi Arabia. And in India, there is already MOU signed with the Indian Railways to develop the hydrogen trains and focusing on the replacing the diesel trains. And it supports the net zero 2070 target. And also Alstom plans to launch the hydrogen train on the Jind and Sonipat road in Haryana, expecting in 2026. In Saudi Arabia, it's already collaborated with the Saudi Arabia Railways. The Alstom already sent this first hydrogen train to the Saudi Arabia Railways. It's already demonstrated here, the first hydrogen train. And it supports the Saudi Vision 2030 for decarbonization and smart transport. Demo run already have been done between the Riyadh and the Al Majma. It was in 2023. It's a real example of hydrogen trains. Okay, let's come to the digital twin fundamentals. What is digital twin?
Sorry to interrupt, sir.
As of now, we have seen.
Excuse me, sir.
What is? Yes, ma'am. Please.
Sorry to interrupt.
Yes, ma'am.
The
Yeah, no issues, please.
thing you the thing you said in India and also in Saudi Arabia, you have launched a new hydrogen railway system, wherein how we are
Yes.
compromising the or mismatch, supply demand mismatch, compression, liquefaction, and chemical storage, sir. That all adds cost and complexity. No, how you
Of
are
course.
balancing, sir?
Yes, ma'am. Of course, we need more digitalizations, and we need more, the government laws and the government supports to the hydrogen system emerging into the transportation as well as the power grid. There is a lot of challenges. There is a transport challenges we have. There is a production challenges we have. There is a lot of challenges here in this. But even though, as of now, Alstom's, there is no local productions. We export from the France to the India, right? So even though in future the Alstom plans to launch the hydrogen plants in India to meet all the following challenges, like what you are saying, liquefaction and the transportations and everything. That is a major complex system, right? For that, we will go to the digital twin. So maybe the digital twin, how it could help us to meet these challenges.
That's why we are making this forum, so we could find some solutions. So that's it, nothing. Thank you, sir.
Yes, ma'am. Yes. Okay. So as you know, this what is digital twin? As of now, we have been discussing how hydrogen is going to help with the grid stability in power sector. How the hydrogen is helping the railway systems. This is all we discussing this hydrogen alone. So, what is the role of digital twin here? As ma'am requested, there is a lot of challenges we have. How we are going to compete with the challenges with the modern hydrogen technologies. So, the digital twins plays a crucial role. A digital twin is a real-time digital replica of any physical systems, like it's a power system or railway systems or any hydrogen storage or hydrogen transportation. It's a digital, it's a replica of those physical systems. It's such as an asset, network, or process that continuously mirrors its actual behavior using live operational data. And the process starts at the physical layer where the IoT sensor, in the digital twin, we have the key components for the IoT sensors, data acquisition systems, and the cloud edge computing, and machine learning, system modeling, and the connectivity infrastructures and cybersecurity. The measurements and transmitted through the data acquisition system to cloud or edge computing platforms where the data is processed and stored. The digital twin combines this real-time data with the system modeling and simulations, creating accurate of yeah, hello.
Yes, sir, you're audible. Hello. என்ன பாருங்க. சரி சரி.
Can I audible?
Yes,
Yeah.
sir, you're audible, sir.
Yeah, sorry. There is network glitch from my side.
No issues, sir.
I will reshare it. I will reshare it. Is that visible?
Yes, sir.
Okay, thank you. Sorry. Okay. That is, what we are talking about, the key components, right? Yeah. The robust, the connectivity infrastructures ensures this continuous two-way communications between the physical system and its digital counterpart, while cybersecurity layers protect the data integrity and the operational reliability. Together, uh, these components enable the engineers to monitor, analyze, simulate, and optimize the system in the real time, supporting better operational and maintenance decisions. As you know, the type of digital representations, we have the digital model, digital shadow, and the digital twin. Digital model is a static model. There is no real-time data exchange. And the digital shadow, it's a unidirectional data flow, and it's only sharing one-way communications. It can automatically from the physical to digital, and the digital twin, it's a bidirectional. Digital may inform or trigger changes. The real-time data keeps, it's a closed loop control uh, in this technology. Why digital twin for the hydrogen energy systems? So it's essential for the hydrogen energy system, which was very complex, safety critical, and tightly coupled with the power grid. As you can see in this diagram, the physical hydrogen systems, including the electrolyzers, storage tanks, compressors, and the fuel cells, is continuously monitored through the sensors. Measure data flows into the digital systems, where it is stored, filtered, and analyzed. That is why we use the digital twin. And in practically, digital twins allows the real-time conditions monitoring, early fault prediction to reduce the downtime and the efficiency optimizations, and the hydrogen productions and the usages. They also enable the virtual simulations before constructions, improving the design and commissioning. Most importantly, digital twin ensure the safe operations, monitoring critical parameters like leaks, pressures, temperatures issues, while enabling the seamless integration of hydrogen systems with renewables of the power grid. You know, these are the key challenges we can come through from the digital twin platform. This makes the hydrogen systems scalable, reliable also. Let's go to the architecture. How does the architecture would be there? There is a lot of layers for the hydrogen energy systems. The physical layer, normally we call it as actual assets, where the electrolyzers, turbines, and the grid, they're all installed. We replica with the same systems in the physical layer. As I discussed before, the IoT sensor, those sensors are we fixed in the sensing and the data acquisition layer, the data processing and analytics layer. where all the real-time data and the physical assets, it is, it's processing this, all the real-time data here in this. And the model and the simulation layer is a mechanism based models, example, the power flow, dynamic stability, and electrochemical processes. Integration and the interface layers, dashboards or user interfaces, control loops, possibly the automated control and optimization actions. Life cycle modules, designing, planning, operation maintenance, real-time monitoring, predictive maintenance, or scenarios analysis, so expansion of plan. Also, the need of the digital twin in TPSs. What is TPSs? It's a traction power substation systems. The digital twin also helps to simulate the train movement and its load. We can predict the dynamic load variations, train accelerate, cruise, and brake when we can generate when the train can generate the regenerative energy. And also it prevents substation failures also. Simulates the stress on the transformers, circuit breakers, and the feeder lines for proactive maintenance. It can help predict the voltage drops, feeder overloads. Identify the weak points in the traction supply before the actual failures. In the railway sector, we have the power zone and the neutral zone to run the train. So where there is a power zone, it's failed. So that will be a weak point of the traction. We can predict, we can identify that by using the digital twin TPSs. Optimize the schedule and energy usages, analyze the train timetables, regenerability, and load balancing to minimize the energy consumptions, and reduce the downtime via the predictive maintenance. Continuously monitor asset health to forecast the failures and the schedule maintenance. These are the layers in the traction power systems. We with digital twin technology we use this. As you can, the first layer is as always the physical layer, where the physical layer is here, the substations, OHE rails, overhead electricity, and rails, switches, trains. The second one is a data layer, a SCADA, IoT sensor, event loggers, train GPS, axle counters. The axle counters, which means the where the train is located, that is the axle counters, and OHE temperature sensors. The simulation layers, we have the ETAP rail. We have the ETAP rail is a software, and OpenTrack is a software, digital silent, MATLAB. These are the software. We can simulate these data in that software. We can get the output. And we Alstom, so we're using the ETAP rail and OpenTrack for our own train monitoring system. The analytics layer, load forecasting, voltage stability monitoring, energy consumption protections. These are the analytics layer, and visualization. We can visualize all the practical scenarios with this layer. So the TPS digital twin, improves the reliability and our safety and energy efficiency. Yeah. Finally, let's comes to the complete integration from hydrogen, digital twin, and to the power. The digital twin, hydrogen integrated in power sector. Full hydrogen value chain digitalization. Digital twin DTDEC covers hydrogen production, storage, transport, refueling, and usage. Operational optimization and safety. Real-time monitoring and the prediction help detect the equipment issues to reduce the risks. And it's also helps to design and the commissioning the phase benefits. Digital twin simulates the plant, train behavior before the building, making the design faster, cheaper, and stronger. And the system integration with the grid in renewables is, it optimizes the hydrogen production when renewable energy is abundant and helps the balanced grid. And I hope basically I covered the hydrogen, how we integrated the power sector and the power railway systems because the limited time. even we could explore the grid stability. It's a big topic, and also the train traction in the railway system. There's two major topics which I just covered very basic system, basic things only here. Yeah, in case of any doubt, you can ask me.
Participants, kindly pose your questions in the chat box. Sir, excuse me, sir.
Yeah.
This may be
Yes,
a very
ma'am.
basic question.
Yeah.
Don't mistake me. Thing is,
Yeah.
we have been into electric vehicle. That era has been
Okay.
created, and most of the users are switching to electric vehicle. Now,
Yeah.
the
Yeah.
problem is occurring is the disposable of battery. How we are going to dispose the batteries, because battery life is going to be only 2 or 3 years, or at the maximum 4 years, right? We have to change
Yes.
every 3 years once. Now, you're saying electric train, right? That is going to be
Yeah.
powered with hydrogen.
Yes.
There also we need a battery storage. As your session also, or in previous session also, Rajaganesan sir also told that they'll be either with grid connected, or either it. That's why I posed that question earlier, whether
Okay.
you are explaining standalone or grid connected system.
Okay.
For a grid connected system or a standalone system, we are going to employ batteries, right? So already disposal of batteries in queue with the problem. Then how we are going to
Okay.
solve the hydrogen storage and battery problem together if we are going in for a hydrogen vehicle, sir, green hydrogen?
So, your question is how we are going to,
Yeah, yeah.
you know,
I'm asking
the
very
physical
basic
challenges.
question.
Yeah. It's okay. Very basic things is very necessary to look forward. Physically, the challenges between the batteries and the hydrogens, or in the metros or in the EV vehicles, uh, the duration, right?
Yes, sir.
Because the duration is very short. But to meet out that duration issues, we use the hydrogens. You know, if you are using the batteries in the electric vehicles or the trains, the first concern is the battery weight, right?
Yes.
And the EV batteries are heavy, affecting it. It can affecting the design and the efficiency and the range. It is compared to the fuel vehicles, EV. It still have the shorter driving ranges only. And also the another challenges is charging time. The charging time takes longer than refueling, especially on standard chargers. But hydrogen will replace this, right? Because we have the own hydrogen production unit in one station, or like it can be easily refueled. So, and another is a thermal management also. We have to consider this thermal management in the EV vehicles and the trains, because the batteries are very heated. It needs a proper cooling and a heating, and it should affect the performance of the battery as well. And the if it is a harsh climate like extreme temperature, also can reduce the battery performances. Okay, these are the challenges if we are using the batteries in the train and the EV cars. But if you are going to replace the battery with the hydrogen energy, it can the lower weight. The weight is will be reduced, first things, and the range will be longer. The hydrogen fuel cells is offer high energy density, right, compared with the batteries, and it making them for we can use the trains, trucks, and buses also. It can be help you to faster refueling. And the space, next to considering it's a space is right. The hydrogen tanks also can place in the underfloor or over the roof. It can be freeing up the space compared to the bulky battery packs. Bulky battery packs, you can easily use it over roof, using the fuel cells in the over roof. It's very simple in the design wise. And the performance also, the fuel cells, it can handle the cold or hot weather better than batteries, not just like batteries. It can be easily adapting with the worst climate as well. And the infrastructures also, for the fleet, normally we call it as a fleet, like number of vehicles, number of trains in a same time to refueling or charging the batteries. Especially for the fleet operations, the depot-based hydrogen refueling, that's what I told you, depot-based hydrogen refueling. It can be simpler and implement the large scale of EV charging networks. So here we can easily, face the limitations, particularly in range, weight, and refueling time. We can challenge the battery in the future of EV car and the trains.
Thank you, sir.
Yes, ma'am.
There's a question from participant Rana Singh. Which kind of sensor is used? Does this system is doing edge or fog computing? How did you integrate DT platform to it? Time series integration issues, practical integration challenges you faced, data accuracy level. Can it be audit level accuracy?
Where it is, ma'am? It is located in the chat box.
Yes, sir. It is posted in the chat.
Okay. How can I open the chat box? Let me check. Yes, sir. Ma'am, come again, please. Can you please read out that?
Which
I
kind of
couldn't
sensor
find
is used? Does the system is doing edge or fog computing? How did you integrate DT platform? I hope this question is related to time series integrate issues, practical integration challenges you faced, data accuracy level. Can it be audit level accuracy?
Hello.
Hello, sir.
Am I audible?
Yes, sir, you're audible, sir.
Yes, ma'am. Sorry. I can see that now. Which good sensor is used? Does this system is doing the edge for computing? How did you integrate IoT data digital platform and the face to data accuracy level? It is accuracy. Okay. Yes, ma'am. Hello. Hello.
Yes,
Hello.
audible, sir. Yes, sir, you're right. It's audible, sir.
Okay. Okay. I think there is a network issue from my side. Sorry. Am I audible?
Yes, sir.
Again?
Participants, your queries could be answered through mail also. Uh, because of time change from here to there. Shall we conclude the session, sir? Sir?
There is a network issue
Sir,
from my side. I don't know how.
yes, sir, yes, sir. Shall we conclude the session, sir? The queries could be answered through email also, sir. Sir? The queries could be answered through mail also, sir. Or mail or WhatsApp, sir. Shall we conclude the session, sir? நான் ஃபோன் பண்றேன். ரீஜாயின் ஆயிட்டாரா?
Hello.
Sir, shall we conclude the session, sir? Hello?
Hello.
Sir, shall we conclude the
Hello.
session, sir? Hello, shall we conclude the session, sir? அதுதான் தெரியல. அவங்களுக்கு நெட் இஷ்யூஸ் போல இருக்கு. நம்ம பேசுறது கேட்கலையும். சரி, நம்ம கன்க்ளூட் பண்ணிடலாமா? Now I invite. கேக்குதா? கேட்கல. Now I invite Dr. D. Periyalaga, sir, to propose vote of thanks to Hariharasuthan, sir. Sir, please.
I would like to express our sincere gratitude to our esteemed resource person, Engineer Hariharasuthan, for delivering an informative and thought-provoking session during day 3 and session 6. His session provided valuable insights, practical knowledge, and a clear perspective on the subject, which greatly benefited to all the participants. The depth of the content and the clarity of the presentation made the session highly engaging and relative to the both academic and professional practice. We also extend our heartfelt thanks to the AECT Atal Academy for their constant support and to the FDP organizing team, all the participants for their active involvement and cooperation contributing to the success of this session. Once again, we sincerely thanks to Engineer Hariharasuthan for sharing his expertise and for his valuable contribution to the FDP. Thank you, sir. Thank you very much, Engineer Hariharasuthan.
Participants.
One second, ma'am. Shall I allow the start video? Okay, ma'am. Dear participants, kindly unmute your videos. We need a photo session. Dear participants, kindly unmute your videos. We had a photo session.
Hari sir? Sir, am I audible? Sir, Hari
Dear
sir?
participants, please kindly unmute your audios. Video and sorry for the inconvenience. Kindly unmute your videos.
சார் அவங்க பெர்மிஷன் இல்லைன்னு சொல்றாங்க.
இல்ல மேம், அலோ பண்ணியாச்சு. Dear participants, kindly unmute your video. We need a photo session.
ஸ்பீக்கர் இருக்காங்களா சார்?
No.